Continuing on with class 17 in thermodynamics, we get into section 5.2. Now, I'm not sure if there was enough content up to now to justify just having that the stopping point, so I continued. Don't know if that's the wise thing to do, but I did. Much of this stuff as we're going forward is just an introduction to some concepts and ideas that are necessary that every student should know as part of thermodynamics. So it's because there's not examples that go along with them. I often wonder if it's the right thing to do to just spend time hand waving, but let's do it anyway. So first off, we have these two statements that we want to introduce to you. The Kelvin-Planck statement, which reads, "It is impossible to construct a device that will operate in a cycle and produce no effect other than raising of a weight and exchange of heat with a single reservoir." Basically, what we're saying here is that you must have a sink, and that a thermal efficiency of 1 is impossible, right? Because remember, the equation that we had written for efficiency for a heat engine was efficiency is equal to 1 minus the QL over the QH. So if we had 0 QL, which is what's showing right here, we had 0 low heat, we weren't rejecting any heat. We converted it all into work. We would have an efficiency of 1, but that's impossible. So we need a sink. The Clausius statement was, "It is impossible to construct a device that operates in a cycle and produces no effect other than the transfer of heat from a cooler body to a warmer body," right? So this is sort of like a refrigeration type of thing, right? That's impossible to have an infinite coefficient of performance. So therefore, it must be less than infinity. We must have some type of work being placed into here in order to do this, right? So here's two illustrations of this. I'm not sure how much benefit you'll get from here, but this is sort of like, this is a demonstration of the equivalence that these two statements right here, the Clausius statement and the Kelvin-Planck statement, are actually the same thing, right? So they're equivalent statements. The first is a demonstration where we have here on the left-hand side where we're going from a low to a high. This is the Clausius statement where the work is going to be equal to 0. Well, the same thing over here. In order to get the work out of this, we must have some heat rejected, right? I don't know if that actually, and in the book it even says we'll leave this to the student to prove. I don't know if that's a very helpful thing to say, but that's what it also said. Also next door, in another figure nearby, there was the perpetual motion machine of the second kind. And so they said the perpetual motion machine of the first kind is one where you can get energy from nowhere, right? So that was the first law, breaks that one down. This is one of the second kind, and I forget what the third kind is. But anyway, if you're taking a look at here, what we have is we have this heat pump where we're taking heat out of the ocean and we're putting it into a high temperature body, right? So that's going on the right-hand side. That is possible as long as we have work coming in. But then here on the left, what we have is we're taking a heat from the source and somehow turning all of it into work. And that work is what we want to get, but we need to steal some of that work out in order to get the heat pump to move. Well, we can't do that. That's just not possible. You still need a sink right here. You need to go to a sink no matter what. And this thing can't be your sink. So that's an idea of a perpetual motion machine of the second kind, but it is not possible. Now let's change course a little bit and go to the reversible process. All right, so this is an important concept because we were about to talk about the Carnot engine, which is really some of the point of all of this is that maybe we can establish what the best the most efficient engine that is possible. We can come up with it based on what the extremes are. And in order to do that, we have to come up with processes that will enable us, right? So these are going to be idealized processes, the reversible process. And it doesn't exactly exist. None of them exist, but we can come up with the hypothetical. And so this is an example of a reversible process, or an attempt to be reversible process, right? So I think this is actually a demonstration where it's not possible. So this is not a reversible. Okay, it says so right here in the caption. It's an example of an irreversible process. So up here I want to read this. A reversible process for a system is defined as a process that, once having taken place, can be reversed, and in so doing leave no change in either system or surroundings, right? So that's the definition. And let's see if it holds true for this, where we have like a little pin inside of a gas, and this gas is pressurized. And so we pull the pin, and the gas is pressurized enough that it lifts this piston up right here. So we get to this point right here, this stops. There's still pressure inside here. But if we want to push this piston back down and get back to the original state right here, this piston has weight. So as we're going to actually have to apply more force and generate, and the pressure be higher than the pressure right here. So because we are having a pressure through a volume, right, and it's a larger pressure. And you can ask yourself, why is it a larger pressure? Because right now this pressure is sufficient to hold this piston in place. This piston has weight. It is causing pressure onto this thing. But in order to get it to move, we have to unbalance those forces, and therefore we must create more pressure than was at its. So at the same location, anywhere along this line right here, we have to have more force to generate that pressure. So the pressure has to be higher. So it's not going through the same identical process. And then when we pull it down here, in order to be able to get, we put work into the system. In order to get the system back to its original state, we have to remove heat, right? So this can even be thought of as being like the process of an engine, right? Of a heat engine, and what we had to do. Except maybe it's more of a refrigerator, I guess, in that sense. But still, what has happened, though, in order to get it back to its original state, we have to change its surroundings. That's the idea. That's why it's irreversible. Now, a possible reversible process, that has to be done really slowly, is to have this gas that's under pressure, and we remove a little coin, right, or a little weight. And by going sideways, we're not performing any work onto this because we're not changing the potential energy. Our force is not in the same direction as our displacement. Therefore, there's no energy work being done. And so this gas is now going to be allowed to expand a little at a time, a little bit at a time. And so this is an example of a reversible process, that we could perhaps put these coins back onto here, and as long as there wasn't any friction involved, we would be able to get back to our original state. So that's like a theoretical one. Other ones, we might have a frictionless pendulum, right? Because we're changing from kinetic energy to potential energy. Kinetic energy here at the bottom, potential energy where it stops, and it could just keep going forever as long as we didn't have any amount of friction or air resistance, which also, we could heat up the air just ever so slightly by having some drag along here. But if you've ever had most pendulum, you'll see that you'd be able to witness them slowing down and coming to a stop, because there is friction, there is drag. So a quasi-equilibrium gas right here. So if we, once again, if there's no friction, we could perhaps push this in, and probably doing it slowly, and then let it go, and it would return to the original position, as long as there's no losses. But there are going to be losses. But this would be the quasi-equilibrium expansion and compression of a gas. So these are perhaps two close to being reversible processes, even though they're not exactly. Here was another one here that was in Sengel that I thought was interesting. It's a reversible process, deliver the most and consume the least amount of work. So we could have the water is pushing along this movable bulkhead, right? That's moving without friction, and then we can push it back, right? So it's going to return back to its spot. But if you do it fast, this is for the slow one. If you do it fast, you'd have these waves taking place, and you would dispel energy. I mean, you would lose it. So we have to start talking about factors that render processes irreversible, and we would use the word irreversibility. That's a great word. Friction is one of them, right? Where we could see that this block coming up this slope right here, and is being drawn up the slope because of these weights. It gets the top right here, and maybe this thing stops, and then somebody lets go of the weight. But because of the heat that's generated from this friction, we're not going to, we would come back to our stable position, but they wouldn't have as much weight right up in there. I guess maybe that's how you would describe this. But the idea is that the friction is taking away energy, and it's not a reversible process. In the fact of you trying to return this thing to its original thing, you had to change its surroundings, which is the definition of reversibility. Another irreversible scenario is if you had this membrane and you had a vacuum and a gas, and then you puncture, as they're showing it over here, you puncture the this membrane. Well, it's going to be hard to put the toothpaste back in the tube, if you will. You need to have a compressor to be able to do that, and even in the act of compressing this, you're going to in order to return it to its original state, you'd have to extract out heat, right? Because the temperature is now going to change onto the thing. So we're trying to get a reversible process means we go all the way back to its original state. But the system around it, the surroundings, are going to be affected by your making the thing the same. Friction renders the process irreversible. These are probably redundant right here. We're showing fast compression and fast expansion right in there. They excite the molecules, so you are not getting it. You can't return it back to its original state. Let's see. You get a heat transfer through a finite temperature difference. So one thing that we will learn is to make a heat transfer in a reversible manner, you must have an infinite amount of temperature difference, right? So you have to go very, very small temperature differences, because if it's a finite temperature difference, large enough between two bodies, it'll be irreversible. So the heat transfer process approaches reversible as the temperature difference between the two bodies approaches zero. Therefore, we define reversible heat transfer process as one in which heat is transferred through an infinitesimal temperature difference. But here's just like a common sense one. If you if the outside temperature is 20 degrees Celsius and the soda was 5 degrees Celsius, that you can't, if you extracted 20 degrees Celsius from it, this thing would actually, it'd be impossible for this to go down, I guess, with having the same amount of heat extracted. Right, so heat transfer through a temperature difference is irreversible. The reverse process is impossible. You can't go from the cold to the hot. You must go from the hot to the cold. And then mixing. This is more of the toothpaste one, isn't it? Right, where you had oxygen and nitrogen right here, but you break this membrane between them and they mix. You can't get them unseparated from each other without going through some elaborate process. Other factors, hysteresis effects. I don't know if I want to go down that road too far. I always associate a hysteresis, with a curve that looks something along these lines right here. I'm going to draw this poorly. It goes like this right here. I'm going to do this poorly right there. And I think as you go back and forth, you change something. I'm not sure if I wish I hadn't written that now. Could erase it. Could erase the whole thing. There you go. Erase the whole thing. Forget about that. Anyway, usually associated with like magnetism and some electrical things. I'm not an electrical engineer. We can also have loss due to electrical losses. Ordinary combustion, yeah, combustion is hard to uncombust your fuel. And this was just a picture, I guess, that was supposed to be associated with the finite temperature differences, right? So there's an infinitesimal temperature difference that might be happening right here, or here's a finite temperature difference we're talking through there. So this was not the end of this was not great. So maybe nobody will get to this spot in the video. Sure, that's what we're going to do. So we're going to go do some more examples. We'll do some single examples in the next one where, sure.